Bismillahirrahmanirrahim. So today we'll start with the third lecture, and this will be the thermal conductions. And today we'll start our lecture from article number 2.6, and we'll follow the book Principle of Electronic Materials and Devices, written by Kasam. Okay, I have already uploaded this book in your Google Classroom. Now, about thermal conductivity. So, article number 2.6.1, thermal conductivity, right? Okay. So, we know that metals are both good electrical conductor and also good thermal conductors, because we know that metal have some free electrons. Those are known as conduction electrons, and it plays a vital role for heat conduction. So we know that the transport of heat in case of in case of metal is done by free electron or this electron gas. But in case of non-metals, the conduction is due to the lattice vibrations. So in case of metal, these free electrons moves from one positions to another positions, and that one will determine that this one is a very good conductor. But in case of non-metal, we know that each material consists of some lattice. So whenever this lattice vibrate, then the conduction occurs. So when a piece of metal is heated at one end, the amplitude of the atomic vibrations, thus the average kinetic energy of the electrons in this region increases. Okay, that means whenever we increase the whenever we hit it the one end of an metal, then the amplitude of the atomic vibration occurs and the average kinetic energy of the electron increases. So this due to this that means these atomic vibrations, the energy will transfer from one positions to another positions. So these electrons act as an energy carrier. That means it carries the energy from one positions to another positions. So these are the basic concepts. So next, so from here we know that the thermal conductivity of a material uh, implies that the heat thermal energy can transport through the medium. Now, the experiment shows that the rate of heat flow q prime equals to dq divided by dt through a thin section of a thickness delta x is proportional to the temperature gradient delta x divided by delta t divided by delta x and the cross sectional area a. So we can conclude these things. We can conclude these things with this heat flow. Heat flow q prime should be equals to minus a. This small k is known as chi a chi delta t divided by delta x, and this formula is known as Fourier's law of thermal conduction. Look, this formula is known as Fourier's law of thermal conduction. So q bar. So please take a pen and paper and write down these equations. Q prime should be equals to a chi delta t divided by delta x. So this, so you know, this k is the material dependent constant or the constant of proportionality. That one is sometimes known as thermal conductivity. So this k or this chi is known as this chi is known as thermal conductivity. So look, if you look at this figure 2.19, look, we are providing heat from the this left side. So this left side electron or this left side free electron will heat it up and it becomes hot, but the right side one is the same as cold. So these free electrons or this hot electron will vibrate to the next electron. Then this due to this lattice vibrations, so this heat will transfer from one positions to another positions. And also look at this figure 2.20. So we are providing heat. So this one is for a single electrons. So it moves a distance of delta x. Due to this temperature increase, delta t means the increase of temperature, delta q divided by delta t, that means the rate of heat change. So if this one is the first position, so this one is due to the rate of heat change. So from hotter side, from this hot side to this cold side. Okay. Now, so this one is a figure, the electric conductivity versus the thermal conductivity for various materials. So we will learn these things later on. Now, so as because the previous formula is known as Fourier's law, we can derive the temperature gradient delta T divided by delta X. We can compare these things with Ohm's law. Ohm's law, the electric current I should be equals to A minus A sigma delta V divided by delta X. Okay, so here this sigma is the electric conductivity, right? So so this one is the this equation number 2.35 is the Ohm's law of electrical conduction. Now we can compare the relationship between these two equations, that is 2.35 and 2.34, by another formula. That one is known as Whiteman's Franz Lorentz law, and that one is K, or so that one is chi sigma T equals to CWFL. So this WFL stands for Weidmann Franz Lorentz law. So this chi CWFL is a constant terms, and that one is equals to pi square. Now this one is not chi, this one is k, which one is known as Boltzmann constant, pi square k square divided by 3 e square. So this one is the charge of an electron. So we know that all these three parameters are constant. So if we put this all these values, then we found that CWFL equals to 2.44 into 10 to the power minus 8 watt ohm per Kelvin square, and this one is known as, this number is known as Lorentz number. Okay, so this number is known as Lorentz number. So experiments on a wide variety of metals. So these equations, or this CWFL, is derived from different experiments on different metals. Now, if we compare these two equations, if we compare this Ohm's law and Fourier law, then what we can conclude? So we can conclude these things as, sorry, before that I need to also discuss another things. That one is, so here they have discussed about the conduction of copper electrons. So copper has free electrons, and that free electrons vibrate to the next electrons, and this vibration is known as vibrational. This wave is known as vibrational wave, and so that one depends on temperature, and they have discussed about these sort of things. Now I would like to find out this two relationship between the two parameters. Okay, now this one is the thermal conductivity of various classes of material at 25 degrees Celsius. So in the left side these are the parameters, and in the right side these are the chi values. So using these formulas, the thermal conductivity, so in 95 by 5, that means 95% copper and 5% tin, bronze bearing made of a powdered metal contains 15% volume of porosity. Calculate this thermal conductivity. Thermal conductivity means you have to determine the chi value at 300 Kelvin. Given that the electrical conductivity of 95 by 5 bronze is 10 to the power 7 per ohm per meter. So we know that chi equals to sigma TCFL. So from using that formula, we can find out the chi value. After that, as because this one, that one is 95 by 5, so we can, and also that one is a there are powder contains 15% of the porosity, so that we can also find out the effective thermal conductivity using chi effect. So try to solve these things by yourself, and if you face any problem, we can also discuss these things in our problem solving class. Now the next one is very important. So next one is thermal resistance, article number 2.6.2. Now consider a component having a length L has a temperature difference delta T between its two ends. So let us go to figure 2.24. So this one is a 2.24. So this one is a metal, and its length is L, and in the left side it's that means heat is Q prime, and the temperature difference, that means from the temperature with respect to hot side and the cold side, is delta T. Then we can write down that the rate of heat flow, that means the heat current Q prime equals to A chi delta T divided by L. Q prime equals to, so that we know these things from Fourier's law, A chi delta T divided by L. Now if we take delta A chi in the lower, that means denominator, then delta T divided by L by chi A. So I think up to this is clear. Now we know that from Ohm's law we know that I equals to delta V divided by R, and we know that R equals to what? R equals to rho L divided by A, right? We know that what is the relationship between rho and sigma. So the relationship between rho and sigma is 1 divided by sigma equals to rho. Now if we put the value of R, if we compare these two equations and if we put the value of R here, then that one should be L divided by sigma A. So I think this one is also clear. If we use these two formula, then this one will be clear. Now look, if we compare this heat current and this Ohm law electric current, then we found that there is a similarities between this chi and this sigma. Look, there is a very good similarities between chi and sigma. So that one is Q prime equals to delta T divided by theta, where theta is known as thermal resistance, thermal resistance. So this one is delta T divided by the denominator part is known as the resistance part. If we compare these two equations, so the denominator is the thermal resistance, and that one they have denoted these things as theta. So in case of thermal resistivity, that one is denoted by theta. In case of electric resistivity, that one is denoted by R. Okay. Now what the thermal resistivity theta equals to L divided by chi A. So the rate of heat flow Q prime and the temperature difference delta T corresponding to its electric current and the potential difference delta V respectively. Now, if we try to find out the thermal resistance, that one is example 2.20. So, a brush test of electrical resistivity 50 nano ohm meter conducts heat from a heat source or to a heat sink at a rate of 10 watt. If its diameter is 20 millimeter and its thickness is 30 millimeter, what is the temperature drop across the disk? That means you have to find out the temperature drop, that means delta T. So we know that delta q prime equals to delta t divided by theta, or so we can also know about the theta formula. So in case of theta, we need to find out the chi value. So this chi value should be equals to sigma t WCFL. So this value is a constant, and the sigma value for the brass is a fixed. That one is 50. That means sigma value is given 50 nano ohm, and T value equals to 300 Kelvin. So I think all the values are given here. You can, if you try in your home, you can also solve this examples. Okay. So up to this one is your third lecture. That one is the thermal conductivity. So this one will be the end of our uh, that means first topic. That one is, look, our syllabus includes classical theory of electrical and thermal conductions. Here we have learned about the scattering, mobility, resistivity, temperature dependence of metal resistivity, Matheson's roles, and the last topic was thermal conductivity. So this will be the end of our first part, and also the end of our third lecture. So in the next class, we will learn about the introduction to the quantum mechanics, or we will start to learn about these topics. Okay. So, so here I would like to conclude our third lecture. So we can also, if we if you face any problem, we can discuss these things in our problem solving class. Okay. Up to now, thank you.